Good morning, ma. Am I audible, ma? Screen visible?
Yes, sir. Yes, sir.
Okay. We'll wait for 1 to 2 minutes so that people will join. So first experiment, everyone submitted. Good. So second experiment, still 4 people should submit. Huh? Who are the 4 people who should submit? Amrita Kandeshwaran, you didn't submit. Anto Gladson, you didn't submit. Dakshinesh, Vigneshwaran. These 4 people don't did not submit. Second experiment. Third experiment, 1 student submitted. Still time is there. Who is that submitted? I think Amrita Kandeshwaran submitted. Amrita Kandeshwaran, why you didn't submit second one? You submitted third one. Huh? You didn't do second one. Okay. So you try to submit. So you can see here I put that unit number 1, nodes and problems. Right. Go through these problems. First hour I don't want to start these problems. I want to start a new unit because first hour I don't want to waste the first hour. If at all you require problems, we'll do in the last hour, right? Okay. So let us start the second unit. How many people are there now? So 26 including me. Okay, no problem. So we'll start today's session. Again, I repeat, I'm continuing with the. I'll start a new unit now because first hour I don't want to waste the first hour with some known thing. Let us start the new unit. It's a good unit. You will appreciate this unit than the first unit, right? Because there is a lot of what do you call meaning and visualization which should happen for the second unit. Let us start it. So good morning all. I think we completed one unit. Problems I gave it. You can go through it. If any difficulties are there, we can give one session for it. Again, your cycle test first unit is the syllabus, right? Don't ask later. I already informed. So let us start the second unit. The second unit is gas solid non-catalytic reactions. In the first unit, we saw what is the heterogeneous reactions and how the rate is going to be different. What rate you have to write, global rate or intrinsic rate or observed rate or apparent rate. How to write for a heterogeneous systems. We assume that in heterogeneous systems, the reactions are happening in a series of reactions, and we assume some step will be the rate controlling. That is, the resistance offered will be more, and based on that, you will write the rate, right? So let us see the next part, that is gas solid non-catalytic reaction. There is no catalyst. There are two types here: gas solid non-catalytic, gas solid catalytic, right? So gas solid non-catalytic is nothing but there is no catalyst, but there is one solid as a reactant, right? So when there is a solid, gas is diffusing onto the solid, and then the reaction is happening on the surface and in the surface, that is inner pore of the surface. Then how to write the rate, right? So the solid can be a porous. The solid may not be a porous also, but generally, whenever there is a solid, generally the solid will be porous. So the gas should diffuse through the pores of the solid and then go and sit on the inner surface and then react. That is what is happening, right? So when it is like that, then what are the models for explaining its kinetics? There are two models here. One is shrinking core model and progressive core model. We'll see both, right? So, two models. Then volume and surface models. Again, in this, what is the controlling resistances? How to find out the rate controlling steps. The other one is time for complete conversion of single and mixed sizes. The solid, generally we assume the uniform size, but there can be a mixture of solids. There can be a small particle, there can be a big particle. If there is a mixture of particles in the raw materials, how to find out the complete conversion of, if there is a single size or a mixed sizes, how to find out the complete conversion. The other one is fluidized and static bed, that is packed and fluidized bed reactors. We'll be discussing about all this. So let us go into the unit again. At the end of the unit, you will be knowing all that. Gas solid non-catalytic reactions. It can be what generally in our when you are using a derivation, we write for a generalized equation. We write for a generalized equation, and whatever reaction is there, you will be making that as a generalized equation and write the same equation, right? That's how you do it. So the generalized reaction for the entire gas solid non-catalytic reaction is A. We assume A is a fluid, that is gas. Here, fluid can be a liquid also. Liquid, solid reactions or whatever it is in the fifth unit. So in this unit or even in the fourth unit also is same thing. Gas solid, it is catalytic, but here it is gas solid non-catalytic. In both the cases, we assume A is a fluid, that is A is a raw material. Is a fluid here. I'm talking. It is a fluid, generalized term, but actually the fluid here it is gas. Fluid can be a liquid also, but generally in second unit and fourth unit, whenever I talk about a fluid, that means it is gas. B is solid. B is the stoichiometric coefficient of the reactant B. Generally, gas solid reactions, in the sense gas is A, B is the solid. So some small b coefficient of the reactant B gives you. So gas solid, in the sense the reactant only I'm talking about. The reactants are gas solid. When there is a gas and solid, the product can be any of this. The product can be a fluid products. It can come as a gas products. It can come as a solid products also, or it can come as a fluid and solid products. So any of the three can happen. If there is a fluid in the sense it is gas here, but a generalized term I will use a fluid. A fluid plus a gas, a solid, when there is a reactions happening like this, the product can be a fluid, or the product can be a solid, or the product can be a combination of both. Yeah, you can give examples. If there is a gas, if there is a solid, what is a fluid fluid product, like C plus O2, like, or O2 plus C, that is carbon plus O2 gives you CO2. CO2 is a fluid product because CO2 is a gas. Correct. Like that, you can get a solid product also, or you can get a combination of both. Here we assume that the coefficient of the gas molecule is 1 and the coefficient of the B, that is the solid molecule, is B. If in the reaction it is 2A plus 3B, then you can generalize to this particular thing. You divide the entire equation by, I'll just write here. We are writing here a generalized expression. Now, if the reaction is 2A plus 3B gives you some product, this is the reaction happening. And if you want to get this standardized form, this is the standard form. This is the standard form. If you want to get this reaction to this standard form, you divide this entire equation by 2. Then A plus 3 by 2B gives you product. So here the B is nothing but 3 by 2. It's not a 3. Understand? Because when you are going for a standardized form, A coefficient should be 1 and whatever coefficients are there, it is the B. It is not this coefficient. Since A is having 2, you divide that, therefore B becomes B by 2. So in the equation, if you are getting some B term in the derivation, so B is nothing but for this equation, it is 3 by 2. Like that, right? So I'm writing for a generalized equation, not one particular set of equation. Am I right? Discard. I'll just discard. Yeah. So A plus 3 BB gives fluid, solid, or thing. There are two cases here. What are the two cases? The solid, since reaction is happening on the solid by the gas, two things can happen to the solid. Either the solid can change its size, or the solid may not change its size. Correct. So two cases, the particle size remains unchanged during the reaction. Only thing what happens is carbon or whatever it is, so the solid, the hard solid may become porous because the gas is coming out. So it will make a holes in the gas solid and then come out. So that can happen. Or the solid itself will change its size. Initially, big solid can come. So here, when you see here, the solid initially, if it is diameter is this. So at the end of the reaction also, the diameter will be same. The diameter will be same. That is, it is not changing its size. But when it is changing, initially the diameter may be like this. With the time, the solid particle can come like this, or it can go. Entire thing gets reacted, then it becomes like a dot. So the diameter of the particle here, it can reduce. So these are the two cases which we have to see. When there is a solid and there is a gas reaction on the solid, either the solid can change its size or solid can have the same size. So depending on that, because why you can ask me why this is important, size is changing or size is not changing. Because your rate is writing on the surface of the solid. On the surface of the solid, in the sense there should be a surface area. The surface area will come from the diameter. If there is a less diameter, then the surface area will be less. Area is less, then accordingly rate will change. Understand? So that is why we will much bothered about the diameter of the particle. Right? So we'll see now here. Yeah, you can see here. Let us assume, let us assume the solid particles remains unchanged during the reaction. This is the first one. So solid particle, we'll see both the cases. In the first case, the solid particles remains unchanged. When the solid particle remains unchanged, what will happen? You see, this is the initial particle, initial unreacted particle. With the time, after some time, partially converted, finally fully converted. So this can be a hard solid, or this can be a porous solid, or this can be a porous, or this final product can be a hard also. You never know. But the size is going to be same. Size is going to be same. Only the inner reaction is happening inside, and then the entire solid is getting converted to the product. The solid particles contains large amount of inert materials which remain as a non-flaking ash. So there is no ash which is formed at all. It's not like a carbon particle, coal, you are burning it. When you burn coal, the outer surface gets ash, right? This is not that type of reactions where the solid, when it is getting reacted, maybe it contains inert materials or whatever it is, there is no ash formed at all. Therefore, the size remains same. That is what he's giving you here, which remains as a non-flaking ash, or a firm product material which is formed by the reactions. The product which is formed is holding onto the surface, and then it becomes has a hard and unchanged in size. Whatever diameter initially is here, initial reactant is this much diameter. After the time t, that is final diameter, also it is going to be the same. So this kind of reactions, we tell the particle size remains unchanged. When the particle size remains unchanged, the diameter of the particle is not going to change. Therefore, only R is the, if the R is the diameter or capital R is the diameter, final product also will have the diameter of capital R. Understand? Let us see the one more case. The next case, what kind of, we'll see some examples for this, where the size is not changing with respect to the time of the reaction. You can see here some examples like roasting of sulfide ores in air, ZNS, 3O2. This is the A, right? This is the A and this is the B. So if you want to give into the standardized form, you have to divide this by 3 because A should be 1, right? So ZNS plus 3O2 on oxidization, that is zinc sulfide, gives zinc oxide SO2. So here you see gas and a solid is there, or a fluid and solid is giving you both the solid and the gas. Similarly, here whatever ZNS size is there, ZNO is also have the same size. There is absolutely no size change in the size. Iron pyrites, Fe2S2, 11O2 gives Fe2O3. Here also there is absolutely no change in size. Again here, the solid and gas is giving you fluid and gas products, right? The other example is metal oxides to corresponding metals. Any metal oxide Fe2, Fe3O4 on H2, that is reacts with hydrogen to give you iron ore, iron and H2O, right? This also absolutely no change in size. These are some of the examples of that. We'll see some more. Yeah, okay, you can see here the solid plus gas is giving you a solid, only solid, right? This can also happen. Nitrization of a calcium carbide. So calcium carbide on with the nitrogen will give you CaCH2 plus some carbon, which is amorphous in form. You can have different treatments of carbonous matters. C plus O2 gives CO2, 2C plus O2 gives 2CO. Now here you see solid plus gas is giving you a gas, right? Whereas in the previous case, solid plus gas is giving you solid and gas. So these are some of the examples of that, right? Now let us see the second part. This is where the interesting thing will happen. The particle size changes with the progression of the reaction. Initially, the diameter of the particle is this. Initially, the diameter of the particle is this. You can see big particle. So what will happen? The A is sitting onto the what do you call, on the surface of this particular solid. Then it starts reacting, which is you can see a flaking ash which is being formed. The reactor, you can see the size diameter is changed from here to here. Afterwards, you can see after some time the size is changing. After some particular time, the entire reaction is happening. So there is no literally size of the particle, right? So complete conversion we call. So the particle is changing its size. Particle is changing its size. The particle shrinks with the time, finally disappearing, right? So this kind of reactions also will happen. So some examples of it is carbon disulfide from the element C plus sulfur, carbon plus sulfur, so gas and solid at a temperature of this temperature will give you carbon disulfide, which is a gas. So earlier itself I claimed here, right? It can form a gas, a fluid plus solid. It can form a fluid property or a solid property or a fluid and solid property. So I showed you some examples of fluid and solid. Now I'm showing some examples of fluid, right? You can see here. So these are some examples of fluid, and you can have solid also. That is what I'm showing you here, right? So you can see C plus carbon plus sulfur will give you CS2, or the manufacture of sodium cyanide from the sodium amide. Sodium amide is liquid because I'm giving it is for a fluid, so it can be a solid, liquid, or a gas. There are some liquid reactions also happening on the solid. Will give you again the property. Products can be a fluid can be a gas or a liquid, right? So one more example is sodium thiosulfide from sulfur and sodium sulfide. You can get sodium thiosulfide. These are some of the examples where the solid which you are using, it reduces in size, right? So we saw here when there is a solid which is being present, the solid can change its size, or may not change its size. When the solid is not changing its size, then it is forming the ash which is being formed, or whatever it is. It will be binding to that particular solid itself. Whereas if it is changing in with respect to the reaction, the size, then after at the complete conversion, there may not be any solid which is present in the reaction at all, right? So to represent these two models, one is size changing with the reaction, the other one is size uniform, that is size changes with the reaction. Here size is not changing with the reaction. We have to give some models how to model this kind of reactions and how to model this kind of reactions. For this there are two models. One is progressive core model, progressive conversion core model, you can call whatever you name, progressive conversion or progressive core model, the shrinking unreacted core model, right? So some people call this progressive core model, shrinking core model, right? So progressive conversion model, unconverted, right? So shrinking unconverted core model, PCM and SCM. So both are very important. If you assume it is progressive core model, you can model your reactions as one particular thing. That is, you get one equations. And if you are assuming it is shrinking core model, then you will get some other equations. But generally, which is better? Progressive core model or shrinking core model? So generally, shrinking core model is very famous because your realistic problems or realistic equations, generally they go for it follows shrinking core model. We'll see both. What is this, right? So the closest representation of the reality which can be treated without too many mathematical complications, there are two. One is progressive core model and shrinking core model. The name itself suggests progressive conversion model. So slowly the conversion is happening. Shrinking unreacted core model, right? So we'll see that both, right? I'll take some 1 minute break. I'll just come. Yeah, we'll continue. So we are discussing about the kinetic models. There are two models which gives a representation of the two whatever types. That is, one is size changing and the other one is not size changing. So both the models can be depicted by these two models. One is progressive conversion model, the shrinking unreacted core model. We'll see both. What is that? First, let us see progressive conversion model, that is called as PCM. Right? So, what does this mean now? Now you see. Yeah. Now, what does this mean? The reactant gas enters the reactant throughout the particles at all times, most likely at different rates at a different location within the particle. The solid reactant is converted continuously and progressively throughout the particle. That is why this is named as progressive conversion model. So I'll repeat again. The gas reactant enters the reactant, the reactant gas enters and reacts throughout the particle at all times. So you can see here, this is the initial solid which is having low conversion or no conversion at all. The entire solid is being wetted or whatever you call it is by the reactant gas. That is what he's giving you here. The reactant gas enters the and reacts throughout the particle at all times, right? Throughout the particle at all times, and most likely at a different rates at different location within the particle. So here the rate may be different, here the rate may be different, inner rates may be different. That is what is assuming here. In a progressive core model, the reactant gas reacts the particle at all times. The other one is the solid reactant is converted continuously. Now you see, initially there is no conversion. After some time there will be some conversion, and finally a highly converted product you are going to get. Right? Highly converted, what do you call, product or raw material. Highly converted raw material in the sense it is a product, right? So what are these? What are these, right? So let us write this particular thing as a function of r, right? As a function of r in the sense it is the diameter. Always capital R will give you the diameter of the particle. Yeah, let me write something here. Now let us assume this is the center of the particle. Let us assume, because this is the symmetry, because it is a spherical particle, always generally whenever there is a spherical particle, your boundary conditions what you put is generally you take at the center. You won't go from here. You won't because this let this is 2r. Let you are having a diameter of 2r. So when you are having a diameter of 2r, you never tell that r is 0 and r is 2r. Your boundary conditions, since it is symmetry, what we do is we take this center as 0 and we assume this is r, small r, and we assume this is smaller, capital. This is a capital R and this is capital R. So the entire radius will become 2r. That's how you will do in all the spherical particles. You never take like this. It is 0 and then this is 2r. Instead of that, you take the center as 0 and then do symmetry, right? So the total will be 2r, whereas we go only for this because whatever is happening here, the same thing is happening is here. That is what we generally assume. Not only here, even in heat transfer, when there is a spherical particle, the heat is conducting. You take the same assumption. Whenever there is a spherical or even spherical, cylindrical, everything, right? So let us assume this is 0 and this is small capital R and this is capital R. That is, the outer surfaces are having at a capital R. Now this x-axis I am taking as the radius or the diameter,
What is on the y-axis? Y-axis I am taking as the concentration of the solid reactant. So initially, the concentration of the solid reactant, this is the original concentration. You know what is the original concentration of the solid? Let us assume that is the highest, because the solid concentration goes on decreasing because reacting, right? So initially what will happen is the outer surface, let us assume after some time, the reaction, the core will be here. The reaction, more reaction is happening here, less reaction is happening here, less reaction is happening here, because everywhere throughout the reaction, throughout the solid, the reaction is happening, but not at a same rate. That is what we are just assuming here. The reactant gas enters and reacts throughout the solid particle at all times, more likely at a different rates at the different locations, because it should penetrate through this particular thing. In that process, you will have some resistance. Therefore, there is no penetration here. There is just a sitting here. But if the particle should go here, it should penetrate through this particular pores. So in that process, the rate will be different because the time it is taking more. Therefore, the rate of here and the rate of here, it will be different. So when there is different rates, there will be different conversions also, or different concentration of the solid. So let us assume here the concentration is maximum because not much of the gas is coming and reacting here. Therefore, the solid concentration almost it literally remains the same as the original. Whereas at the sides, what is happening is the sides gets reacted. Therefore, you get a parabolic profile like this. There's a symmetry, right? So whatever is happening to this, the same thing will happen here. So you are getting this. So the solid is reacting, therefore the concentration is getting dropped of that. Whereas in the center, there may not be a reaction, much reaction. Therefore, the concentration will be higher. And again, concentration drops in this particular half. Generally, we go only for half, one half, not the entire one, right? Here he is showing entire one. Now, after some time, let this is time some 1 minute. Let it be 1 minute. Let this is time t0. If t0, what will happen to your concentration profile? It will be absolutely like this flat, correct? Because there is entire thing is same. There is no t0. T at after some time you get like this. T at maybe around 5 minutes. Let I'm taking some example here. It can be any time, right? So you can see the concentration is getting dropped because the solid is getting converted, but the conversion is not uniform. Here it may be converted fast, here it may be converted slowly. Therefore, in that process, your profile goes much like this. That is, the center again will have higher concentration. The edges will have a less concentration, but that concentration drops from this particular thing to here, right? In this particular type, this much is the concentration drop. Now let t is infinite or maybe 20 minutes. I'm just taking some example here. It can be any number here, right? So what will happen now? After some time, what will happen? Even the core inside also gets converted, may not be fully converted. Now you can see here, literally the sides, entire conversion is happening. Therefore, not much of concentration is there, but center there may be a bit of more concentration. So there will be a huge drop from the original concentration. Therefore, what you are going to get is a product or highly converted reactant, right? So which the size is not being changed. So here you can see here, according to the progressive core model, the reaction proceeds continuously throughout the solid particle. Now you see, throughout the solid particle, the reaction is happening. Entire, even in the inner core, right? That is what we call it as progressive core model. Progressive core model. So the reaction is happening not only on the surface, even in the inner surface, but the rate may be different from the outer surface. That is what you assume here. Again, I repeat here. You can see here. The reactant gas enters and reacts throughout the particle at all times, most likely at a different rate at different locations within the particle. The solid reactant is converted continuously, progressively throughout the particle. So the solid particle is continuously converted and progressively converted, right? We'll see the other one now. Let us assume shrinking core model. What is this shrinking core model? Now the assumptions of it is, I'll just repeat. The reactant first begins at the outer surface of the solid particle and the deeper layers do not take part in the reaction. This is a big statement. This is a big statement. That is, the outer inner layers is not taking part in the reaction. Only the reaction is happening on the outer surface. That is what he is assuming. In shrinking core model, you are assuming that if this is the solid, the gas is only coming onto the solid and then the reaction is happening only on the outer surface, not on the inside. The gas is not at all penetrated inside initially. Whereas in progressive core model, what you assume is the gas is sitting here, the gas is going here, the gas is going here. Entire of the solid, it is getting reacted at a at continuously, but at a different rates. But here, what he is assuming is the solid is only reacting at the outer surface. When it is reacting at the outer surface, the inner part may not get reacted at all. That is what is that until the reaction first begins at the outer surface of the solid and the deeper layers don't take part in the reaction unless or until all the outer layer has transformed into a solid or a gaseous product. So what is assuming is this, the solid is like this. The solid, this is the gas molecule. What is assuming in this is the gas, the solid which is present at the outer surface first gets completely converted. Once it is completely converted only, the next diameter or inner surface gets reacted. This inner surface won't take part in the reaction unless the outer surface completely converts. That is what he is assuming. Whereas in progressive core model, we assume that the reaction is taking place inside the reactor also in all the times. Right? Gradually, the reaction zone then moves inward into the solid constantly, reducing the size of the core of unreacted solid, leaving behind completely converted solid and an inert material. So you understood what he is telling? Is reaction is happening. The reaction is happening. Once the reaction is happening, this product is formed, and then only it is going to the inner core, like this inner core, like this inner core, like this inner core. So if this reaction to happen at here, this core, the reaction should happen. If this core reaction is happening in the sense, outer core should happen first. Outer core should happen first. Only once this core is finished, then it goes to this core, then it goes to this core, then it goes to this core. It is just like peeling onion. Understand? So if you want the reaction to happen at the core of the onion, outer surface should be peeled first. Then only you can see the inner, right? It is shrinking core model is just like onion peel. Whereas in what is that other progressive core model is not thinking that there is a layers inside. The reaction is happening in the entire onion, on the entire onion, or even the inside the entire onion, right? So we'll show you that now here. Now you see here. Try to get. Now can you give me what is happening here? Yeah, profile. Yeah, anyone can give the profile. What is happening there? Yeah, please. Here, one important thing is here I am drawing a parabolic profile, where here I am drawing no parabolic profile at all. and here you can see the change of the size. You can see here different. Here I'm writing like a straight lines. Yeah. Any idea? Now what is happening here? Can someone explain this? Yeah. I explained the earlier one, right? Now you think and then explain.
So maybe this is a non-porous particle, so it has to start from the outside and then.
Let us not assume it is porous or non-porous. Let us assume it is a solid. Whether it is porous or non-porous, that will come later. Now, till now, I never talked about the porous or non-porous. Yeah, let us assume it is a solid. Either it is porous or non-porous. No problem. Yeah. What is happening here? How you can, what do you call it? Describe this particular diagram? Yeah. Anyone else?
So the gas molecules are uniformly reacting at the surface.
Good. Then what is happening? What is happening here? Why you are getting like this straight line? Why you are getting the straight line? You see the diameter of this straight line is getting reduced. Yeah. What is that all that?
Sir, since the inner core is not reacting, the concentration throughout the inner core is equal.
Very good. Very good. Yeah. Yeah. Can you still talk more about it? Yeah. What you thought is absolutely correct. Yeah. Then what is happening? What is this? What is this? These two. Why there is a big gap here? Still there is a big gap. Yeah. Can you talk something
Sir,
on that?
since they are reacting, therefore the concentration, there is no concentration of that particular solid.
Okay. Good. Good. Any other people? Yeah. Any other? What is your name, man? Who talk? What is
Sir,
your name?
Rishita, sir.
Rishita. Okay. Anyone want to elaborate on Rishita's thought? Did you understand what she taught? What she talked? Yeah.
Sir, the outer layer is gradually reacting to the it is exposed to gas, so it is reacting with the gas. So the concentration of the solid in the outer layer will be less. So that's why there is a gap in between those two lines. But in the core, the concentration of the solid will be uniform throughout. So there is a horizontal line on the top side.
Who talked? Shweta. Who talked? No?
Yes, sir. Yes, sir.
Oh, good. Any other thought? Any other thought? I am asking you, as Rishita told, absolutely correct. Why what she is telling here? But why there is a straight line here? There is no concentration here. There is no concentration here. Your profile is like this. Your profile is like this. Sorry. Your profile is like this. Like a U, what do you call, inverted U. Here you can see the profile is like this. There is no profile here, any profile. Whereas here the profile is here. You can see the darkened line. Why there is no concentration profile in this region? That is what I am asking you.
So because it's completely converted to the product. Like
Super.
The reactant concentration is 0. So it's completely converted as.
Concentration is 0. Good. Absolutely correct. Yeah. Any other people can generalize these two thoughts of what Hirshita told and other girls, Sweta and Sri Vignesh told. Yeah. Can you summarize and then give? Yeah. All three thoughts are correct. Now can you summarize and give what is happening? How can you describe this diagram? Yeah, you can read here. According to the shrinking core, the reaction proceeds at a narrow front, which moves into the solid particle. The reactant is completely converted as the front passes by. what is that means? That is what you three people talk. Now, how to decode this? Yeah, how to decode that?
So as the gas pass through the
Go ahead. Who is talking?
gas molecules move into the converted
Converted or unconverted? Don't get confused.
converted product, sir. Converted product.
Okay.
Then it
Converted
starts,
product is the product. Unconverted product is the raw material. Correct?
unconverted is the core part.
Yeah, core. Tell me now. Tell me what you are telling.
Then it moves to the core part and starts reacting. So we get the
Yes.
final.
Okay.
Final.
Now,
You know.
yeah, you see here. This is the initial solid particle which is having a low conversion or time t is equal to 0. So, where is this pen? Yeah. I am assuming this is the center of a particle and this is the R, sorry. And this is the capital R. Capital R is nothing but the radius. Capital R is the radius, right? So my profile will be, this is the ash layer. If there is some conversion, what will happen is this forms a product which is the ash. In ash, completely the solid is converted completely. Therefore, there is no concentration of the solid. That is why it is literally 0. Here, there is unconverted solid. Therefore, the concentration will be equal to the initial concentration. This is the initial concentration in all the things. So the initial concentration. What is happening here? I don't know why this is all coming, starting to come. 1 second. I'll again come back. Yeah, now you can see here. Hey, what is happening? This without me writing anything, it is just yeah. How to delete that? The moment I'm taking here without me writing anything, it is start. Yeah. Oh God. Hey. Okay. Let us not use this pen. I don't know what. So this is the initial solid concentration in all the 3 cases, right? Whereas in the previous one, this is the initial concentration. The initial concentration is reducing, but here the initial concentration is reducing in this particular axis, right? So in this axis, the initial concentration is decreasing. But here you see the initial concentration is decreasing in this particular length. So initially it is like this. After some time, this product is formed. There is no solid which is being present. It is a what do you call product or ash we call. The ash layer, sometimes it can be removed from it or it can stick onto it. Let us assume it is sticking onto it. Therefore, the outer core now becomes here. Outer core becomes here. So the gas should penetrate through this and then come only into this particular inner core. That is why there is no concentration here. And then again, the concentration is same here because it is just like the concentration of initially because it is not converted at all. So if you still, after some time, you can see this is the complete product which is formed. This is the unconverted. This is having the same concentration as the initial. So if the reaction should happen, what is happening here? According to the shrinking core model, the reaction proceeds at a narrow front. Only the front which is being exposed to the solid gas, the reaction is happening, and the reaction will proceed along with the core. As the core is getting shrink, the reaction front also is moving according to the shrinking of that particular core. Yeah. Reactant is completely converted as the front passes by. As the gas is passing through it, the reactant is completely converted. Unless the reactant is completely converted, the gas will not move to the next front. Understand? That is what this assumption. Now, these two assumptions are there. It's around 9:25, 5 more minutes. Now, tell me, visualize what is happening for a coal. Now, you take a coal and burn the coal. What is happening? Whether shrinking core model it is forming or progressive model it will depict. Yeah, that burning of a coal through which model is much familiar to us. Either it is progressive core model or shrinking core model. Yeah, I told both the models now. I'm giving some examples now. Coal burning. You take a coal, solid coal. You are burning the coal. The burning of a coal, whether it is, you can imagine like a shrinking core model or a progressive core model. Yeah. I gave some example. Yeah. Let us choose out of two, one. What you choose?
Shrinking core, sir, because the ash is.
Form.
Yeah,
Okay.
the ash is formed.
If the ash is removed, then what will happen? Now ash is formed as you tell, correct. Now what I'm doing, I'm blowing some air and then removing the ash. There is no ash here now. What will happen?
It'll just start shrinking again, sir.
Shrinking again, right? So
Yeah.
whether it is in a shrinking core model or progressive core model.
Shrinking core.
Shrinking core. Any other idea, ma? Any other thought? I'll give one more example now. You take a paper bundle, you take newspapers, tie the bundle, tie the newspaper, maybe around 1 week's paper or even whatever 1 month paper. You tie the bundle. Yeah, start firing at all the edges. Then what will happen? The burning, whether it takes place like a shrinking core or a progressive core. I'm just giving an example of paper burning. When you are burning a paper, yeah, what is happening? Whether it is burning like a progressive core, that is there. You are assuming the reaction is happening. The product is nothing but whatever product you are getting. Maybe ash is the product. Yeah. Whether it is going as a shrinking core or a progressive core.
Sir, shrinking core, sir.
Shrinking core. Hirshita, good. I think Vignesh gave some Google Docs. Please fill the attendance. I think 54 people are there. 54, I think, including me. So 53 are there. So those people who came to the, yeah. So I gave two examples. Very good. It is all shrinking core model only. Oh, even though we are having two models, but generally whatever we visualize, all the reactions will happen like a shrinking core model. That is why we generally give a model based on the shrinking core model. That we'll see in the next class, right? That is what shrinking core model. How to model the reactions based on the shrinking core model. Generally, any visualization, what you see, the reactions, it will all happen because of the shrinking core model, right? See, we'll see that in the next class because you require more time here because it's not a lot of discussion should happen because you get a lot of doubts here. I know, so I cannot complete it. We'll see in the next class. So try to read from the book. You will give a lot of information. Don't read this derivation. You go mad with the derivation. Let us not. Don't read the derivation. Only read why we are going for a shrinking core model compared to that of the progressive core model. Okay. With that, I'll stop here. We'll meet in the next class. Okay. Yeah, those people, please give the attendance. I stop the sharing now. Some of you are asked